All right, the last topic in our stoichiometry section deals with heat stoichiometry. Now, one of the things that we've not really discussed is how heat is important to chemical reactions. We know we have a chemical reactions when one of two things occurs. One, there's a color change. Two, possible color change. And two, a definite heat change. And maybe so small we don't notice it, but every reaction has a different heat change, meaning that when a bond is created, heat is being used or captured to keep the electrons within the barrier that we call a bond. When a collision occurs, that bond is broken. Not only are the electrons able to escape, but so is the heat. But as soon as the heat is released and the electrons are quickly moving away, they get attracted to another element with its electrons and form new bonds by absorbing some of the heat or all the heat or excess amount of heat that's available to create the bond. That creates a change in heat. We call that enthalpy. A change in enthalpy, a change of heat, a change of energy, if you will. In that we can measure that by feeling if heat is being given off in a chemical reaction, that means some of the heat release has been absorbed to create new bonds, but the rest of the heat is being moved to the environment, and that's what we experience. A lot of combustion reactions are exactly doing that, meaning they break apart, all this heat is released, a little bit is used to create the carbon dioxide and water, which takes very little energy to make, so that extra heat goes out, and of course we take advantage of that by taking a blower motor in our furnace and blowing that heat throughout the house. Okay, that's called an exothermic reaction. An exothermic reaction means the heat is being given off. Exo means outside, thermal means heat on the outside. The opposite of that is an endothermic reaction. An endothermic reaction is where the collision occurs, bonds released, heat is released, and the new bonds that are going to be created requires not only all that heat, but extra heat from the outside, so it feels cold to the outside because heat has been taken away. We feel a sensation of coolness or outright coldness, like when we have a cold pack in athletics. And so what we're going to do is we're going to look at the mathematical relationship of that with how many particles we have in the reaction. This is called heat stoichiometry. Okay? Now, let's take this reaction. We have the production of ammonia this is a synthesis of ammonia by reacting nitrogen to hydrogen and creating ammonia, and the result is a negative 30 kilojoules of energy. In other words, the amount of energy required to hold these molecules together is greater than the amount of energy that is being held here. And that's represented by this graph right here. Our reactants have all that pent up heat. We call that bond energy. There's actually a potential energy. That potential energy we call bond energy is stored within the molecules here. When the reaction occurs, then it becomes kinetic energy and then restored as new bond energy. And the amount of bond energy to have ammonia is a lot less than that of the reactant. So we can see a drop in the heat. The drop in the energy required to create those bonds. And that's why we have here the negative 30, because it's a drop of 30. So we call this an exothermic reaction. Now, in this diagram, this is called a heat content diagram. Which in Chem 2 you're going to be making some of these, but just follow along on this right now. We can draw a line between the two plateaus that represent the reactants of the products. It looks something like this. As you get into the nuances later on in chemistry, we find that it typically does more of something like this. And this has a specific meaning right here, the difference between the top of the pump and the level, but we're not going to get into that. But that's called activation energy. But, we'll get to that in Chem 2 for those of you who decide to get into that. But that change right here from this level to this level represents your change in heat, your delta H, and that, because it's negative, that means it's an exothermic reaction. Okay? Now, the other direction is what we call an endothermic reaction. Endo means within, and of course therm means heat, so the heat stays within it and it grabs even extra outside of it. And so that means that at the plateau, in this case the reaction is with nitrogen and oxygen, which turns out to be an endothermic reaction. It's a positive value, which means the heat levels go up from reactants to products. So it's absorbing heat, and when this reaction runs, if it's being kept in some kind of container, you can feel the contents change. You'll feel the outside of the container to be cold. Now, because this is positive, that means the change is going up. This is called an endothermic reaction. And again, we could draw a straight line from here to here because in terms of chemical bookkeeping, that really is what's going on. But if you take a nuanced approach where you can see the details here like we did last time, this is going to look something like this. And that heat, that little bump there, of course, is your activation energy, which we're not going to get into, like I said. But the difference between the reactants and the products, which is shown here, it's called the delta H. Delta is the Greek letter for D, which stands for difference. You're subtracting the final minus the beginning. The top minus the bottom is positive, where the other one above that was lower minus higher, which was negative. And so we have here an endothermic reaction, where it's the products minus the reactants is positive.